So in Chapter 8, we're going to continue to build our understanding of conservation of energy, and we're going to do this starting with another type of force. We have the force due to a spring. The Hooke's law force is equal to negative k times x. Now in Chapter 7, specifically example 7.4, we found that the potential due to a spring, U, is equal to 1/2 kx squared. And we can plot this in a graph. So we have a u-axis, u as a function of x, versus x, position. And if we graph this, we see a little x squared shape. What this is telling us is how the energy of this particle, of this spring, changes as a function of its position. So for x equals 0, the spring isn't stretched. Remember, x is the stretch of the spring. No stretch means that I have no potential energy built up inside of this spring. And physically, that makes sense. If I have an unstretched spring, then it's not going to move at all. It has no potential to make things move. As I move away from this 0 point, as I stretch the spring towards a positive x, or I compress the spring towards a negative x, the spring builds up energy. It builds up energy and wants to spring back to its natural position of 0 energy. So this kind of motion that you get from this spring, this graph represents that motion, which is called oscillating. And if we return to what we know from conservation of energy from last chapter, we know that the total energy of a system, E, is equal to K plus U. In the last chapter, we dealt with U being gravitational potential. Here, we can change the form of that U. We can have our regular kinetic energy, 1/2 mass times velocity squared, plus our potential energy due to a spring, 1/2 k x squared. And this really shows us conservation of energy, all depicted in this graph. And we can tell a lot about our motion just from this graph and this conservation of energy equation. So let's take a closer look at that. So let's look at a spring in terms of the types of energy it has when it's stretched and when it's completely unstretched. We know energy is equal to kinetic plus potential. So we have kinetic when I'm stretched plus potential when I'm stretched has to be equal to kinetic when I'm not stretched plus potential when I'm not stretched. I have kinetic when I'm stretched equal to 1/2 mass times velocity squared plus 1/2 k times x squared, the amount that I'm stretched, equals 1/2 times mass velocity when I'm not stretched squared plus potential when I'm not stretched. When I'm not stretched out, I can see right here my spring is at its natural length, so x is equal to 0. There's no stretch, which means that I have no potential energy due to the spring. The spring doesn't want to move because I'm not separated. I'm not displaced from my equilibrium point. So in the no stretch position, all I have is kinetic energy. In the stretched position, if I pull out my spring so that it's stretched as much as humanly possible and let it go, right when I let it go, it's starting from rest. So this means it has no initial kinetic energy. I only have spring energy. So what this graph is trying to show us, what we're trying to see, is that the energy changes between being entirely potential in the spring, which gets converted into speed, into kinetic energy. And if I want to see where this point occurs on the graph, I can see at x equals 0, I have no energy. No energy from the spring, so no potential energy. But I started with some energy, so this means that all of my potential has been converted into kinetic. So I have a maximum amount of kinetic energy at this point. And if I take my derivative of this graph and set it equal to 0, I would find that I get a maximum in kinetic energy at this 0 point. So this graph is really showing us that energy changes forms. That I can take a bunch of potential and convert it into kinetic, and I can take that kinetic and I can convert it back into potential. So thus far, we figured out how we convert forces into energy. Forces become energy through doing work. Applying a force over a distance gives us our gravitational energy, U equals mgh, and our spring energy, U equals 1/2 kx squared. These two types of forces, gravity and spring force, are what we call conservative. This means that the net work for a round trip is 0. Round trip work is 0. This is in contrast to another kind of force that we've looked at, a force called friction. Friction is non-conservative. What this means is friction actually loses some energy. We dissipate energy in friction due to heat. This energy loss happens because friction always opposes motion. So therefore friction is always going to be negative when compared to your direction of motion. We can generalize these kinds of forces, these kinds of conservative forces, to find a generic equation for finding potential from a conservative force. In general, the potential due to a conservative force, we'll do it as a function of x, is equal to negative integral between the initial position and the final position of the force acting in whatever direction it's supposed to be acting, times the derivative of that direction. So potential energy is the negative integral of force. And we can differentiate this to find that the derivative of the energy with respect to the position will then give you your force back. So conversely, force is the negative derivative of potential. These are good shorthands for remembering how to switch between forces and energies. And to get some practice with this, I suggest you look at checkup number 8.1. So there are multiple different forms of energy, And what we've discussed so far is mechanical energy and how it's conserved, but this only happens if the force that's acting is also conservative. In the case of friction, friction is non-conservative. We'll call friction a non-conservative force. Does this mean that energy goes away? It doesn't. It actually means that energy is dissipated, is lost, and in the case of friction, it's lost, it's converted, it changes the form into heat energy. It turns into tiny thermal motions, microscopic thermal energy. So this gives us different forms of energy that we can convert between. We can convert between chemical energy, we can have nuclear energy, we can have electrical energy, we can have magnetic energy. All these different forms of energy can combine together to make sure that your energy is always conserved. And all of these really are just different ways to think about mechanical energies. They are all the same quantity, they're all energies, they're all measured in joules. So energy form can change, but the total amount of energy remains the same. And one of the most complicated things in physics is tracking all of the energy that's lost due to heat, figuring out where that extra energy goes, usually in the form of non-conservative forces. One of the most amazing discoveries in physics happened in the early 1900s with that awesome energy discovery. That discovery meant that energy conservation actually comes straight out of mass conservation through the following formula developed by Einstein. E equals mc squared. Energy is equal to mass times the speed of light squared. And what this told physicists, what this tells us today, is that energy can be converted to mass. And mass can be converted into energy. And it's this principle that allows our nuclear reactors to work. What we do in a nuclear reaction, we take what I'll call heavy uranium, and we break it down into light uranium plus energy. So we take some of the mass that's inside of this heavy uranium, some of this heavy uranium mass, and we convert that into energy and a lighter form of uranium. This is how we get nuclear power today. The final point to make in this chapter, a very short chapter, is how we actually use energy, how we dissipate energy, how we do work, and that's in the form of power. Power is defined as the rate that we do work. So this is work expelled divided by the time that it takes to do this. So we can rewrite work. Work is a force times a change in position over a change in time. And a change in position over a change in time is just velocity. So power is equivalent to all of these things. Power that you get from a source that's doing work is work divided by time, force times a change in position over a time, or a force times a velocity. If I want instantaneous power, power at any given instant moment, I need to take the derivative of work with respect to time. Doesn't really change the equation that I'm using, just changes how I apply it. If I want to know the units of power are equal to the units of work divided by the units of time, which would be a joule divided by a second, which we give the name watts. So your light bulbs, the power that measures the power in your light bulbs, watts, is a unit of work that the light bulb does divided by how long it takes. We can also rebrand work in terms of power. We do this in example 8. And we find work is equal to the integral over time from T1 to T2, however long you're doing that work for, of the power times dt. All of these approaches to describing power in terms of work or in terms of forces are equivalent. The one that you use depends on your needs, depends on what you actually need to calculate. They're all equivalent. They can all be used. It just depends on your needs. And to get a good handle on that, you'll just need to do the homework, do some practice problems.